So we're gonna, only three of you?
There's still one.
Okay, right. Then we're going to start, yeah. Right. So let me start with from introducing the jury members. Please, Professor Wen.
各位同学大家好，我是中原大学的温文义教授。你好。
Thank you.
同学好，老师是从军官校来的，谢谢各位大家。
大家好，我是刘忠伟，从中山大学来的。
Thank you.
中山大学。
施教授从中心大学，中心大学是。我是中军刚是的，I'm going to be the chairman of this session. And next, I'd like to invite each team to introduce your team and team member. Start with your reporter.
So, hello everyone. I'm the team leader of the previous teams. My name is Jason Lee, and this is Amy. This is Carol, and there's one still on the road. His name is Brian. Thank you.
Right. Thank you. Opponent, your turn.
Hi, and we are Newgate from KGHS. My name is Evangeline Yan Yuwen, and this is Du Ziyi. This is Liu Yishen. This is Cai Youzhen, and this is Wang Peiqi. It's nice to meet you guys.
Great, thank you. Here comes the reviewer.
Hello, we're MG5, and I'm Sean, and Wang Yiyan, Mai Mingyu, Xie Youyu, and Wu Rizhong.
All right, thank you. So we're going to start it. And first of all, I'd like to remind all of you, you can take your mask off while you are talking, right? And afterward, you can just put your mask back on. And so first stage is that the opponent got 1 minute to challenge the reporter for the problem. You may start. Of the available problems on the platform.
We choose problem 13, Ponyo's P2.
Problem 13 is challenge. Reporter, you got 1 minute to make decision.
We'll choose to send the time.
What was that?
We'll
You accept it? Problem accepted. So reporter, you got 5 minutes to prepare for your presentation. Oh, yeah, yeah. Please write down your name of the representatives on the platform, please. All right, reporter, you may start your presentation for up to 12 minutes.
So, honorable juries and fellow competitors, good morning. So, I'm the reporter from Shenzhen High School, the P16. And now, I'm going to report problem 13, Cornell's P2. And here's the problem statement. A gas tube with a seal top is filled with water and melted vertically. The bottom end of the tube is immersed in a beaker of water, and a short segment of the tube is heated. So, investigate and explain the periodic motion of the water and any vapor bubbles observed. So, we'll focus on the formation of the periodic motion and the parameters that will affect the periodic motion and the scale of vapor bubbles. And here's my outline. So I'm going to say the observation, theory, experimentation, and conclusion. So here's my experiment setup. So although it looks like not straight, but we have used the vertical measuring instrument to make sure the gas tube is mounted vertically. Then we have the nickel one, that its height is 1 centimeter. And we set the gas tube in a beaker of water, and its temperature is about 28 to 31 Celsius degrees. Then we have the capillary tube, that its diameter is 6 millimeters and 10 millimeters. So here's my observation video. So you can see the phenomenon happen like this. Then I'm going to, the glass tube is filled with water, and when I heat it, the vapor bubble produced. Then the water will expel to the beaker, then jump back to the glass tube, and it started to process. And Pownell's heat tube, or you can also call it the open oscillatory heat tube. So it is able to transfer heat relative to gravity and use a heat source. So it can happen this phenomenon without any mechanical parts. And here's my theory. So I'll introduce this by using a nuclear heating. So if I heat the glass tube, there's some hole on the glass tube, then the cavity will create bubbles. So then it will grow via evaporation of nearby liquid. So the vapor bubble will become bigger. Then it is a bumping, and this temperature we use the temperature and to minus the temperature of the boiling part. So we can see the trend like this, and so the critical radius we can the vapor bubble critical radius we can see like this. Then we can use this formula to get the vapor bubble's radius. Then let's see the dynamics of water film. So water film will evaporate to vapor, then the vapor bubble will grow. And we can use in the ideal gas equation to get how the vapor bubble produced. So and then we can use this formula to say how the film thickness equation. How long? Yeah. And here's my experimentation. So first, I changed the heating temperature. So the temperature of microwave, I used the 250 Celsius degrees and 350 Celsius degrees. So here's my control variables. I will control the length of the glass tube and the diameter of the glass tube. And third is centimeters from the top of the tube. So it will affect the scale of the vapor bubbles, then and oscillating of vapor bubbles, and the cycle of vapor bubbles, and the fourth is pressure. So you can see the 250 Celsius degrees. It will knock down. The water will knock down. Then later I'll talk how this happened. And this is how its vapor bubbles happen. So where internal temperature is 100 degrees. Then here's the 350 Celsius degrees. So first you can see the foam part. It produced like this. Then in the middle part, you can see the vapor bubbles last longer, and it will oscillating bigger. So and in the rear part, the vapor bubble will exceed the water level in the glass tube. Then it downward the tube and slip back and started to oscillating. And there are also a phenomenon. That is, if the pressure is too high, so it'll boom. Yeah. Then let's see our 350 Celsius degrees, and we found a trend like this. The cycle of vapor bubbles produced becomes longer. That's because the bubbles, if I heated it to the rear part, the bubbles will last longer. And because the glass tube will become harder and it will have more energy, so it can let let the vapor bubble starting to oscillate, and the vapor bubbles will become bigger. So it will have a longer time to produce vapor bubble. Then we also found a formula, a formula like this. We can use this to get the cycle of the vapor bubble. Then why does the vapor bubble will knock down? But just in 250 Celsius degrees. That's because 250 Celsius degrees, it needs more time to reach the boiling part. So the energy increase so the water has enough time to has a heat convection that it can have more energy. So it can knock down to the downward the tube. Then it's a bumping. So at the boundary, it will start to escalate. Then let's see. So according to the video that I showed you before, the vapor bubble, when the vapor bubble exceeds the water level in the tube, so the water will all downward the tube. Then, but it will suck back. That's why, because the vapor bubble didn't have enough pressure to resistance the water, so the water will suck back into the tube. So, and another variables, I use the heating position. So we have the centimeters from the top of the tube. That is nickel wire. So we have 10 centimeters and 15 centimeters. And here's my control variables and dependent variables. So it will affect the cycle of vapor bubbles and the pressure. Then the centimeters from the top of the tube in 10 centimeters. So in this video, you can see it also have the water will knock down. But also we found that its produced vapor bubble frequency is higher than the 15 centimeters, and the pressure is lower than the 15 centimeters because it didn't knock downward to here. It just knocked downward to here. Then we also have independent variables. So it's the diameter of the glass tube. So we have 6 millimeter and 10 millimeter. And so it will also affect the cycle of vapor bubbles and the vapor bubbles pressure. So the 10 millimeters, we'll found that a phenomenon that didn't happen before. So the water will slowly downward the tube and just under here to escalating. So that's because, so why it just slowly downward the tube? So because its diameter is too large to have capillarity. But if I use the 6 millimeter, I have the I can use the capillary to catch the water. So if the diameter is too large, so it'll happen. The tendency is for stratified flow pattern to occur with the liquid flowing in the top of the pipe, and the vapors is in the vapor bubble is in top of the pipe, and the water is in the bottom. So here's my conclusion. This is my experiment setup, just as I said before. And here's I use the formula to know how to produce the gas and the thickness, the film thickness equation. Then just the 250 Celsius degrees, the water will knock down, but the 350 Celsius degrees will not. Then, so the 10 centimeters from the top of glass tube, the bubble frequency will higher than 15 centimeters, and the pressure is lower. So, and 10 millimeters diameter, it has stratified flow. And thanks
All right, thank you. Opponent, you got 2 minutes to ask questions to reporters. Start now.
Can you tell me how the device you hit the tool?
How device?
The device you use for hit the tool.
Support call.
How do you hit the tool? Because you said you can control the temperature like 250 and
Yeah.
300.
We use the power. Yeah. We just use the power supply to control the elect.
And how did you track the bubbles movement?
Sorry, can you say that again? Can I answer the last question? The nickel one will cause the heating. Yeah. We use the gas tube.
And are you sure the whole device is the same temperature?
Yeah. Because I use the temperature to that machine to make sure the nickel wire keep measure the nickel wire.
You done? Okay. All right, you've got 3 minutes to prepare for your next presentation. Opponent, you may take the floor for up to 4 minutes, follow with discussion in the rest of the time.
dear judges, dear defendant, today I'm the opponent from your gate, and I'm going to talk about the problem 13, homeless issue. So, just the reporter says that there is liquidity, heating, and the water dynamics. And they use the temperatures like heating temperature, heating position, and diameter. And their conclusion is 250 Celsius has pumping and lower height has high frequency and low pressure, and the large diameter has stratified flow. So their advantage is their value and tune is great, and there has good explained the theory, and their experimental videos is greatly support their theories and conclusion. And in the chart they show the results that as we saw the error bars are too big. And maybe they can explain the phenomenon by statistics.
So you're going to move on to discussion? Or?
Yes.
All right, reporter?
So our first question is, how do you calculate the electrical resistance of your wire? Like you said, you can control the temperature, but do you think the wires can affect the pixel you want?
The wire will. So you mean that?
Like you might have other factors to affect your temperature, like
But that is no need because we just need to measure the temperature.
and so where do you measure your temperature? Just where do you put your thermometer?
I use the temperature meter to measure the wire.
I don't. So my question is, where do you put it on your
On the wire, the nickel wire. So when I talk about the missing points, just like you say, if the whole device is the same temperature, but that's not. I just answered wrong. That's a mistake. So according to the problem statement, it say we just to heat a short segment. So there's just that short segment will to heat a high temperature, and it's not the same to the whole device.
So can you explain the formula more clearly, like in your part?
Oh, so in my favorite part. Oh, so so first I talk about how the vapor bubbles produce. So the cavity on the small vapor bubble will together and to grow via evaporation of the nearby liquid. So it will become the bigger vapor bubble. Then this trend is show the vapor bubbles how it will will be like. And we measure the temperature that this temperature is the bumping temperature for about maybe for about 105 Celsius degrees above. Then to minus the temperature of boiling part.
So in fact, we asked for the formula in the former page.
Oh, okay, that's okay. So you want to see the particle radius or the liquid film? The liquid film.
Can you
Both of them.
explain the Hawking formula clearly?
So start from here. Okay, so it's the vapor bubbles. We can use this formula to get the vapor bubble radius. So in this formula, you can also see the pressure will affect it, and the temperature that we just get from here also affects the radius of vapor bubble. And also the time is important. Here just a time. So and then we can use this to know the critical radius of the vapor bubble. Yeah.
And so you mentioned that the bubbles movement is caused by is like that because of the pressure is not enough. But do you think the cold water below will affect its movement?
Yes, it also affects this.
So let's go back to the previous questions. You should be testing the water instead of the wires. Because you can make sure that the whole device has the same temperature.
No, because we heating that area, but it will have the heat convection. Or you mean that that segment of the water will be the same temperature, or you mean the whole tube? Just that part, or just that part segment? No, because we use the nickel wire to heating the gas tube, so the water film just on the gas tube will more hotter than the water inside in the middle of the tube. So, and because of the water on the gas tube is hotter, so it has the evaporation. And there's some maybe like hole or any on the gas tube, so it'll have the evaporation to produce vapor bubble.
Yeah, so you can't control the temperature inside the tube.
So,
Because you said you measure the temperature outside, like the wire is outside the tube instead of the wire inside.
so the thermometer in the thermometer in the tube will affect the bubble. So in the next.
Okay, then. So the next question, how do you calculate For the sixth question, why do you think it has to do with the gravity, the movement of the bubble?
You mean this? Why is so the pressure if I need to get the pressure, it also P is low G edge, so it also has a G. So the gravity will also affect the bigger or smaller of the pressure. So it will affect the whole phenomenon.
And how do you calculate how much the bubble moves? And like what application you use for tracking the bubble's movement?
Oh, bubbles movement. We use the tracker to see the bubbles. And so how to you mean that how do I define a bubble? Oh, so we need to a bubble. We need to just exceed. We'll see the whole experimentation. So in this video, so the vapor bubble, the bigger vapor bubble always exists like here. So we also see another vapor bubble. We also see it needs to reach this point, and so then I'll make sure then I'll see it is a vapor bubble.
The size changes, and how can you continuously tracking the bubble?
How to
Track the bubble because its size will change.
the size. Oh, so we see the top of the vapor bubble. So this and downward the vapor bubble it has a manicus. So we see this in a vapor bubble.
But the size changes.
Oh, the size changes. So we'll see the biggest time that the vapor bubbles biggest time to see that it is a.
Excuse me, time's up.
Okay, thank you.
Opponent summarize the discussion for 1 minute.
So we asked how did the porter calculate the electrical resistance of their wires, and they say they did not need to. They don't need because they can calculate the temperature. And how do they calculate the temperature and whether to put the thermometer? They say they put it on the wire and they can use a power supplier to control it. And they say they use tracker to measure the bubble size, and they only measure the biggest bubble in their experiment. And that's it. Thank you.
All set? All right. We only got 3 minutes to ask questions to reporter and opponent. Reporter and opponent, take the floor, please.
Can I do for your video 350 degrees? So did you do the between 250 and 240.
Oh, yeah. So the vapor bubble in 350 Celsius degrees will bigger than the 250 Celsius degrees. When it started to produce the vapor bubble.
And how do you think what will happen when that between 250 and 350? Just the experience that the temperature between 250 and 350. And what do you think will happen?
I think the bubble will get bigger and it will last longer.
And I see number 12. Yeah, number 12.
Number 8.
And 23. Okay, so did you know how the meter is that?
You mean how do I know the diameter is?
Because it's too large, and so how many is diameter?
You mean need to happen this phenomenon? So how bigger the diameter will happen this phenomenon? Oh, we didn't measure that. We just use the
Okay.
centimeter.
And what do you think?
I just think it's a good
Just the diameter.
I think the
Excuse me, time's up. Review, you've got 2 minutes for preparation. All right, review, you may take the floor for up to 4 minutes. Excuse me, you may take the mask off if you like.
Okay. I'm the reviewer from team MVP1 and problem statement. Investigate and explain the predictive motion. And I think the advantage is that we report the fair explanation of phenomena in observation video and well-structured presentation, and the solution is better typography and logic clear explanation ability. And for the advantage is that good imposing manner find out detailed mistake of the reporter X social person and probably answer to their own question. And the suggestion is that they mention a lot of the defined but not the data or the shape. In the discussion, the opponent said, "Are you sure the whole equipment is at the same temperature?" And the reporter say yes. And opponent asks, "How did you calculate the electrical resistance of your wire?" The reporter said that they think that it's not important. And where did you make sure your temperature? And the reporter answered at the wire. And why do you think it has to do with the gravity? It will affect the pressure. And the opponent asks, "How can you calculate how much the bubbles move?" And the reporter said, "Temperature." And how you define? The reporter said the maximum length of it. Thank you.
You done? All right. Concluding remarks from reporter for 2 minutes.
So I'm going to remark. So first, we could try to find more relationships between the formula and data. So and I didn't. We should try to explain more clear about the phenomenon because I didn't let the opponent or reviewer to understand my explain. So I'll try to explain it more clear. So and we should reconsider the effect or gravity. So like just opponent just ask this question and actually I think we should think more about it. So then my experimental, so we could try to measure different parts of the tube and water. Because my variables is not enough to maybe prove my theory. So and we could change more about the temperature and diameter to get the trend. And thanks for the opponent and reviewers suggestions, and thank you.
You done? All right. So comes to questions from jury. Questions, yes.
First question to the reporter. You will consider this as a periodic phenomenon. So where does this periodic characteristic come from?
First is periodic.
Yeah. Why is it periodic?
Okay. Where the periodic come from? Oh, so let's see the sorry. Let's see the video. So like 250 Celsius degrees when it's maxed out, then knocked out and the water slipped back, then it'll happen like this, the vapor bubbles. And after vapor bubbles happen, there's the water will all slip back to the top. Then it'll not happen at that time. So after and for a while, there's this phenomenon happen again. Then that's a cycle.
So why is this time scale the same? Periodic means they have characteristic time. Periodic means you have the fixed time to repeating the phenomenon. Why the time scale are the same?
Why the time scale are the same? Because the heat.
So the question to the opponent, what's your opinion?
At first, the whole tube is filled with cold water, and at first the period might not seem as regular as the latter period.
So for review,
Okay, so the reviewer, how you evaluate their answer?
I think that the bubble will go out things down and will get back to the same place. So every time you will have the same period.
Okay, thank you.
All right, any more questions?
Yeah, I would like to follow on Professor Shi's question. Means for any periodic motion, that is your system at least it has a periodic driving force, or say where is the inertial or where is the restoring force? What is the source? The restoring force, something like that, or the modulated force, liquid vapor interface.
Similar questions for previous.
Yeah. Could you specify what is the restoring force?
What is the
Restoring.
restore?
Oh, you know what, maybe I'll follow up the question. I believe you use tracker, right? To check the motion of the water, the bubble.
Yeah.
You have data graph to show this periodic behavior and how long it persists for this periodic motion. Do you have any data for that?
Yeah.
Okay, if no data, you can answer the previous question.
So just the data to.
No. What caused the oscillation?
Restoring force.
What caused the starting?
Restoring force.
Restart and.
Restoring.
Yeah.
Restoring force. Maybe I should ask the.
Okay, yeah, Dolan, you're gonna comment or answer?
So that's the heat, the heat that.
Oh, you want to repeat the question? The question was, what caused this oscillation? I mean, the restoring force, was that from?
I think the heat.
The heat? Okay.
Answer from the reviewer.
Reviewer and
Because the bubble is the top of the in the top it will go down, so it will have restoring force.
So you mean that how the water slips back into the tube?
Something like that, or the front has oscillated down with some sort of restoring force to make the front back to the initial place.
The pressure.
you, okay, well, time's up. Here comes the scoring time. All ready? Okay, let's go for reporter. Start from me. 7, 5, 7, 4, and 5. Let's go for opponent. Start from me. 5, 5, 6, 6, and 5. The last one for reviewer. Start from me. 4, 3, 5, 6, and 5. I think this much even single I said single. So we're going to take a break for 10 minutes and come back. First couple in 10 minutes. So it's about time to start second stage. All right, should we begin? Hold on, we've got 1 minute to challenge the reporter for the problem.
You can,
Number 9. Number 9 is challenge. Reporter, you've got 1 minute to make a decision. What is the problem? Number 9, oscillating screw.
We accept the challenge.
Problem accepted. Reporter, you got 5 minutes for preparation. Oh, please write down your name of the representative on platform. You?
Yes, I started.
Well, before you started, I'd like to remind all of you, taking video, pictures are not allowed in this room. All right? Don't use it. All right, let me start.
Dear judges, challenger and reviewer, I'm Evangeline from KGHS Newgate, and today the problem I'm discussing is oscillating screw, problem 9. This is my table of contents. First, I will talk about problem statement. Next, I will explain the theory and equation. Third, I will talk about our experimental equipment and results. Last, I will talk about the discussion and conclusion. So first, this is the problem statement. You can see the video from here. When placed on its side on a ramp and released, a screw may a screw may experience a growing oscillations as it travels down the ramp. And the problem told us to investigate how the motion of the screw as well as the group of these oscillations depend on the relevant parameters. Okay, so next page. Oh. So it looks like this. Yes, and as you can see, it would experience a growth of oscillations. And this is the theory and equation. So we use the energy conservation equation, which is mgh equals 1/2 mv twice and squared, and v equals square root 2gh. And after all of these equations, we can get our velocity and our time and also our height. So this is our experimental equipment. First, we have a plastic board over here, a huge plastic board, and we put a protractor at the bottom to control the angle of the plastic board. And third, we put a recorder at the bottom of the plastic board so that we can see the whole oscillation. And instead of a screw, so from the beginning we used a screw, and then we found out that the screw is too small to observe. So we made another equipment, or you could say thing, that we try to make it like a screw. So the screw has like 2 points. So the screw it has a huge circle over here and a small circle over here. So we can just simply put a small plate over here and a big plastic plate over here, then use straws to connect it. Then it would be just like a screw. And first we experimented the different angle of the screw and the board, and we did 9 angles, and then we found out that in specific angles it would have a growing oscillation like this. So when the angle gets bigger, then it will experience a smaller growth of oscillation. And next we experience the different deflection angle of the screw, and here are the 3 graphs. We simply compare the 2 oscillations, this one, and this one. Then after calculating, we get the results. So we can see that when it is over 60 degrees, then it won't have a growth of oscillation. Instead, it will have a decrease like this. And when it is on 50 degree and 40 degree, it will experience a growth of oscillations. The third one is that we experience the different angle of the board. And we have 45, 60, 20, 45, 60, 15, 45, 60, 10. And 45 is the angle of the screw, the big one and the small one, like I just mentioned. Over here, the different angle of the screw and the board, we just control it at 55. And the second number is 60, which is the angle of the board and the angle of the board and the screw. And the third one is the angle of the board and the angle of the board, yes. And we, after experimenting, then we found out that only in specific angles can this oscillation growth be observed, which is when it is at 10 degrees, then all of the angles of the screw that we put down can be observed of growing oscillations. And when it is at 15 degrees, then we can observe that until before 60 degrees, it will all have a growth of oscillations. However, when it is at 20 degrees, the board and the board has 20 degrees, then it can only be observed oscillations at 40 degrees or below. And last, we got to our conclusion. So the first one is the relevant paraments. And we found out that the relevant paraments is the angle of the screw and the table. And it will have an increase, like I just mentioned at the beginning. This one. So with the angle growing, then it will have a bigger growth of oscillations. And the second one is a decrease, where we put a deflection angle. And like the former picture, this one. So before it's, when it is below 60, then we can observe a growing oscillation at 50 and 40 when the angle is smaller. And the last one is at a specific point. It's the angle of the table. So when the angle of the table is only at, when it is at 10 degrees, then we can not observe any oscillations. And when it is at 50 degrees, we can experience oscillations from 10 degrees to 60 degrees. And when the table is at 20 degrees, then we can observe the oscillations at 10 degrees to 40 degrees. And that's my presentation. Thank you.
All right, thank you. Questions from opponent to reporter for 2 minutes?
Okay.
Reporter, take the floor, please.
So, first, that I didn't see your page number. And I want to ask that, did the experiment for the material of your board, did it change the board of the material of the board?
No, we just simply actually use the same board. Yeah.
Okay. So your experiment is just change your angle.
Yes.
Okay. And for your screw, the material of your screw and the real screw isn't the same.
Yes.
And do you think that it will matter?
No, because this oscillation is actually just depend on the radius of the big circle and the small circle. So we don't think that the material would affect the results.
Okay. But for its material, its end won't be the same.
Can you repeat again?
For your screw and the real screw, that their end won't be the same. And a value of that.
Oh, actually we control it by using, because it would affect the results, but that is only when we change our screw-like thing. So when we use the same thing, then it won't affect our results.
And I want to ask that, you have a page that is all about the number, but it is your experimental data. Do you have a theoretical data for it to prove your experiment is right? Do you have a theoretical value to prove that your experiment is right?
Like in this page, then we can simply see that.
Excuse me, time's up. Opponent, you've got 3 minutes for preparation. Conan, you may take the floor for up to 4 minutes and proceed to discuss with reporter for totally 14 minutes.
Okay. Okay. Good morning, honorable judges, my commissioners, and my panelists. I'm Brian Xue from Team ND5, and today I'm going to challenge number 9, also latest group. And this is the problem statement. And we didn't see their main focus, so we won't talk a lot on the problem statement. And for their theory, we saw that they have some formulas for their speed, their position, and their setup is to change their angle of their experiment. And okay. And for conclusion, we asked some questions at that 2 minutes, but we didn't get the answer that we really want to get. Okay, thank you.
So
Thank you.
you're going to proceed to discussion?
Huh?
You're going to go into discussion session? Or?
Yes.
Okay. Reporter, take the floor, please.
Okay, we think that your screw and the real screw has their material isn't the same, and their friction coefficient won't be the same. It will has matter.
Okay, maybe we can draw a picture. So, actually, when it oscillates, the friction is like this, which won't be affected by the material. Like it's a circle, and when it oscillates like this, it has the same definition of here.
But their material isn't the same, so
Yes.
their friction won't be the same.
Yes, but actually it's just a circle. And also, even though the material isn't the same, we just simply control it throughout our experiments. And the statement actually just asks us to observe this oscillation. So even though we just use a simulator, it would have the same oscillations as a real screw.
Okay. And I want to add that what you use to analyze your data. Maybe a trickle or something.
Yes, okay, I'm drawing a picture. Like we got like this, 2 plates, and then we put a dot at over here, and then we use tracker to track.
Do you have the data of your tracker? Oh,
This we
okay.
can, yeah.
Okay, so I want to ask that in my opinion, I didn't see that there is any trend or something in those pictures.
Can you repeat it again?
I didn't saw any trend in your data.
Like we use tracker has another function that it can calculate when the picture is like this and over here, then it can calculate actually how high this is and this one is. Then we would like if this is A and this is B and we have 3 oscillations and this is C, then we would put in an equation that's A over A, B over A, and C over A, then we will compare these 3 and then get this picture.
And you say that you calculate this, but what is the meaning of it?
Because the statement asks us to find out the oscillations, how much it grew. So when we calculate it like this, then we can know how much each of it grew, and we can get this picture. Yes. And I guess I need to explain the number under the picture over here. Like we have a board over here, and when we place the screw, it's like this. So when we place the screw over here, that we have line from 0 degrees to 90 degrees. And the angle that we put down the screw is the second number. So we have x, y, z. And the first number is the angle that we put down. The second number is this one is 1. And x is the angle that we have. We have a board. When we put the screw that we made on the board, it will be like this. And x is, this angle is x. And the angle of the board and the floor, this angle is z. That we show in this picture and this picture.
Okay, for this picture, I want to add that this data is for your experiment, but I didn't see any theoretical theory data.
Oh, this is actually just a phenomenon that we observe during our experiments, and we think it's worth sharing and discussing.
But for your theory, it's to calculate some data, but I didn't see any data. You didn't calculate the data.
We found out that it's only at a specific point. Like for this picture, we want to find out which specific points that we can see a group of oscillations. And we have it over here. We put it at the angle of the table is a specific point instead of the pyramids inside the theory.
Okay. I want to see the page. Next. This one.
Yes.
What did it mean for this?
This data is, we want to find out which, because actually friction affects the oscillations. So we want to, because when it falls down the board, it has two ways. It has x and y. So the x is the oscillations and the y is the friction that it falls down. But if the friction of the board and the screw is too big, then it would experience a decrease of oscillations. So we found out that only in 40 degrees and 50 degrees, when the friction is not that big, small enough, then it would experience growth of oscillations. And when it is at 60, when it is at 60, then it would just simply flip over and can't experience growth of oscillations.
Have you tried 55?
Yes, but we found out that 60 is the points that can't, so we didn't show the statistics on this picture.
Okay. And well, I want to, but in your 40, there is a change here.
Yes,
And what makes it? What makes this?
because the velocity is bigger, so the growth and the increase of its MGH would increase a lot, which is more than the first oscillation.
Have you tried to calculate the data?
Yes, and this is the results. Like we put the picture over here, like this one. So this first one and the second one has a more bigger growth than the first one. And it is, this phenomenon can also be seen in this picture actually. You can see from like some of the picture, if you zoom in, and you can actually see a turn also.
So for this picture and the last picture,
Yes.
it's about the experiment. I
Yes.
mean the real number that you calculate.
Oh, we didn't show it here, but we did.
Okay.
Like the one I mentioned used in the tracker. Yes, we have this number and we just put it in Excel and then we have this picture.
Okay. I'm done.
Okay.
You done?
Yes.
All right, I'm going to summarize the discussion for 1 minute.
very good experiments. I think that maybe they can do more experiments, like maybe change the material of the board or the thread density. So, and we think that maybe they can try to calculate their theoretical value to have a compare with their experimental value. Okay, I'm done.
All right, here comes the question from reviewer to reporter and opponent.
So thanks for the discussion from the reporter and the opponent. And here is the reviewer from the physics teams. And here I'm going to ask all of you guys, what is the main factor of the oscillation? We go first.
The reason is, it's MGH and 1/2 MV square, the change between it.
Like, it is a translational velocity, but what I'm talking about is the oscillation, like it has an angular velocity.
Yes, and
So what causes that?
the oscillation is because the different radius of the big circle and the small circle. So when it has the same.
So like the different velocities on each wheels,
Which one?
like so you mean like the two wheels has different velocities?
It has the same. It has the same angular momentum, but it has different radius. So it's the length that it travels is different. So it will have oscillations.
What do you think?
We think that one is their MGH and the other is their friction.
Friction. So what friction is this? Like kinetic friction or the static friction? Or it's just rolling?
Sorry.
Like, do you think the motion of the screw is just rolling or they're sliding?
Maybe because of the gravity is a little bit slide.
Okay, so what do you think? Sliding, rolling only, or the sliding?
There's also sliding, like we showed in the picture. It has X and Y. So
So-
it's actually slides down.
So if it is sliding, you should consider the effect of the
Friction.
kinetic friction.
But we just changed one parameter at a time. So the friction of every experiment is actually the same. And the friction that affects is only the amount of oscillations that it has.
Like what I mean is like you need to consider the effect of the kinetic friction, not only the static friction like in your presentation. Like have you done like in your theory
Yes.
also? Like did you mention the kinetic friction force?
Kinetic friction force. It's like the kinetic friction force and potential friction force.
Excuse me, time's up. Review, you got 2 minutes for preparation.
Jason Lee from team the physics teams, and I'm going to review problem number 9, oscillating screw. So here's the problem. So here's the summary of the report. They think that the reporter thinks that the biggest factor of the whole motion is the angles. So they did a lot of investigations about the angles. And for the theoretical models, they only investigate about the translational energy, but lack of the explanation and the investigation about the angular velocity that it forms. And also for their experimental confirmation, they showed us that in their experimentations, growth only appears in small radiusing angles of the screw, and also the phenomena only appears in specific angle of the table on the method. So here are some pros and cons about the reporter. They got a clear delivery and good frequency, and also they showed us some clear graphs for the phenomenon like the angular velocity of it and the translational velocity of it. But also they didn't investigate about the oscillation and the friction force, and they didn't explain the graph well. And also the lack of the definitions of the parameters in one of the page. And also they have wrong explanation about friction, because in our reviewer's view, we don't think that the friction will be the same on different wheels. So here are some summary about the position. The opponent thinks that to remake a screw may affect the result, like it is different from the friction force, and also they think that the important lack of the investigation about the material of both the screw and the table. And they also mentioned that in some of the graphs there are some uneven rises and falls and causes inaccuracy. So here are some performances about the opponents. They did pointed out some flaws during the opposition about the reporters, like some of the mistakes they made during about the friction force, and also, but there are lack of the opposition about the theory, like they didn't ask more about it. So here's the discussion part. The opponent asked, does the alternation of the screw affect the result? And the reporter don't think so, because the friction force, they think that it is the same when they changes the screw. And for our reviewer's view, we don't think that it is the same, and the explanation should be confirmed by doing more experience. But if there is sliding motion, it will definitely affect the result, because it will greatly affect the friction force. And also, opponents ask about what causes the rises on the graph, and the reporter answers the bigger velocity when they're sliding down. And here are some of our questions. So first is about the different radius of the circles, and it's the main factor of the oscillation. The reporter thinks that it is about the different radius of the circles, and the opponent thinks that it is about the MGH and the friction force. So in our reviewer's view, we think that the differences of the friction force and radius both affect the motion. And for motion of the screw is rolling or sliding, the reporter thinks that it is sliding, and the opponent thinks that it is rolling with a little bit sliding. So we think that the reporter should consider the friction of both, because we think that it is sliding and rolling at the same time. So it is also related where the energy goes, like where it is distributed. So thanks for listening.
Here comes the concluding remarks from reporter for 2 minutes.
So first, during the discussion, we talked about friction will have a different according to material. But as long as we control the material, this will not have an effect. And also that the statement didn't mention that we can't change the material or do a simulator. And also our screw is a simulation of the traditional screw, but the problem statement did not specify, like I just said. And so that even though friction does affect, and if we use the same simulator, then it won't make our results not considerable. And next is the review. The initial oscillation is caused by different friction acting upon 2 plates, and it goes up to its high point because of their inertia. Yes. And also, there is a sliding motion, and we should have considered the kinetic friction. But since the board was fixed, we don't think that it would affect the results too much and make our results not considerable. And that's it. Thank you.
All right, thank you. Here comes a question from jury members. Yes, please.
So, what's the feature of the screw to be oscillate? It has to be a screw or just two different grades?
It's because two different radius that it will have oscillations.
So a nail will have oscillation.
Can you repeat it again?
So a nail
And now,
would also see the oscillation.
yes, but maybe sometimes it's too small to be observed.
So how about the
We think that it will have a little different, but maybe it can be observed.
For the reviewer, we think that there will be oscillation similar to the screw because the structure of the screw and nail is the same. It's different. The difference is only there are some turns in the stick in it. But in the instrumentation, the stick, the bounce doesn't contact with the plate if they stop. The instrument setup from the port.
Any more questions? Yes, please.
So the proper statement mentioned there's whether you can observe the growth of the acceleration. So I see that we probably mostly discuss the amplitude of the acceleration as you draw in the blackboard. Did you also observe the difference for the frequency, for example, for each different cycle? The frequency change or not?
Both the amplitude and the period has a growth.
So the frequency also grows?
Yes.
You show in your data somewhere?
We can see this in this picture.
It
Yes.
goes?
Yes, there's a growth. But we like
I think you have better one. You have better data. Oh, yeah, that's fine. Yeah, the previous one, I think. Even more oscillation, more up and down data. Yeah, this one. The upper right,
yes.
right?
This one.
You think the period grow?
Like when we use the tracker, we found some has a growth, but some doesn't. Yes.
How about the same question for opponent?
Opponent, any comments?
We think that the frequency will affect it.
No, the question was about the period of this oscillation.
Does it change?
Yeah.
Yes. I think that.
Is that right? You see the data?
Yeah, so but I'm not really understand this
Okay.
whole picture.
What about review?
For our reviewers' view, we think that the current statements say the growth of the oscillation is about the angle that they travel, but it also asks us to investigate what parameters will affect the growth.
No, the question was about the period. Why it oscillate,
Period. So we can't give an exact answer about this.
Okay.
Can I add
Sure,
something?
sure.
Actually, there shouldn't be a growth of the period, but because of the board, there should be a growth of
Should
the
be or shouldn't? Should not or should? So you're overrule your previous answer.
So there should be a growth of oscillations, but because of the different board, so some has it, some different angle of the board, so some can be observed.
But in terms of amplitude or in terms of the period? that's the scoring time. Probably have to take more time to. Take your time, no rush. All right, all ready? Please show your score. Start from me. 6, 6, 6, 4, and 4. And score for opponent. Start from me. 4, 5, 6, 5, 5. Last one for reporter, for reviewer. For me, 6, 8, 7, 6, and 6. I think pretty much needed, so no comment from Joe's number. So let's take a 10 minutes break. All right, so let's start this first stage. All ready? You are? You will? Opponent? All ready? All right, so let's start first stage. Opponent, you got 1 minute to challenge the reporter for the problem.
We would like to challenge the reporter problem number 1, fact of English.
Problem number 1, fact of fingers is challenged. Reporter, you got 1 minute to make decision. Problem accepted. So reporter, you got 5 minutes for preparation. Three. Right, there you go.应该重新开始，很久的。
应该是
没关系。Reporter, you may begin anytime you like. No rush, no rush. Take your time.
自己跳掉了，他自己跳掉了
啊？因为你刚刚赶快重新，我也忘了到底。
他突然就跳掉了。
对，我知道，所以我说我们也不能。
哇！
不能让他吃亏啊。All right, please.
Hello, esteemed judges and fellow debaters. I'm Min Lai, and I'm from MD PH2, and today I'm going to report fractal fingers. And here's my outline. Problem statement. The effects of fractal fingering can be observed if a droplet of an ink alcohol mixture is deposited onto diluted acrylic paint. Are the geometry and dynamics of the fingers influenced by relevant parameters? And here's my setup. Micropipette and scale from 1 to 100 microliters. Pipette holder, white acrylic, and fluidizer to help it more flowable. Ethanol to service the alcohol with proportion 75%. And pigments, we got green colors and red colors ink. We also have the Petri dishes, which diameter is 6 centimeters to serve as the base of the system. And we have the phone and a holder to show a video or a photo to make it easier to put in checker and analyze. And finally, we have the graduated cylinder to help us easily get the right proportion of the fluidizer and acrylic. And for analyze, we have checker and Excel.
And here is my demonstration video. Here in this video, the ethanol in ratio volume is 1.7. The total injection amount is 20 microliters, and the fluidizer acrylic volume ratio is 1.9, and the total thickness of petri dishes is 0.5 centimeters. And as you can see, the first diffusion is extremely complete, and figures are kept into general. And here comes the phenomenal expansion. So we got two expressions. The first one, why would mixture droplet diffuse? So there are two kinds of exercise in this whole kind of fingers generation process. We need to talk about the first initial explosion. First, since ethanol is in polar solvent, so it can both be hydrophilic and lipophilic at the same time. Second, acrylic is comprised of lipids, so this is why ethanol confuses the acrylic itself into whole confusion, and with a volume ratio of dripping mixture being too low, medium, and too high, and it will create a phenomenon. Like this above. So actually this kind of phenomena is pregnant to spreading coefficient, which is also known as the work of adhesion minus cohesion equals to surface tension of injecting liquids minus surface tension of underlayer liquid minus intertangle tension. When spreading coefficient is bigger than 0, then spreading occurs. And first, the initial droplets affected by gravity and shape will change and divided easily through all of time. Second, the ethanol will tend to evaporate and fuse position at thinner parts. And third, after it almost evaporates, parabolic flow starts to happen. It's kind of formula which happens high surface tension liquid pulls lower one, so it will make sure it keeps the balance. And fourth, to minimize surface energy when surface tension is bigger than 0, the droplet diffuses to increase surface area. When reaching 5C, the surface tension equals to 0, then it stops circular spreading. And fifth, to remain minimum surface energy, the droplets retract, causing smooth edge to be finger-like. And we are going to discuss why our fractal fingers and have some, and here are some theories. First is Herschel flow. Velocity-related displacements in narrow gap. There's a thick place and an extremely small gap. It will be displayed by the small one positive. Second is Self-Taylor instability. Tailors in unstable fluids interface in porous medium and it combine with each other. And as you can see, their shape is very similar, and it will mostly have its interaction on the intersurface and porous medium between two kinds of liquids. Finally is carbon homohost instability. By velocity difference across interface of two motivated liquids which are moving of fixed direction, and it will create a shape like this. And the ethanol layer on top is lighter, and solubility of ethanol to acrylic is 1 to 5%. And Herschel flow starts by viscosities. And the unstable displacement is because of Self-Taylor instability. And viscosity is velocity difference is because of carbon compost instability. And two instabilities happen to generate similar shapes. And the tip splitting when curvature reach critical value, the surface tension between finger acrylic will split to minimize the interfacial area to create minimal surface energy. Yeah, and here are our method and results. Our project 1. Each data was median for 3 repetitions. And second, total injection amount is all 20 microliter. And how we measure? First, the average velocity before and after generating figures. We average the longest and shortest radius within 60 seconds, 0.25 seconds per frame. And second, fix x-axis and calculate the slope to find first explosion and second diffusion's average velocity. And average of first layer fingers amount per centimeters plus biggest layer amount. And my experiment 1 is difference of ethanol in volume ratios and dependent variable. First is average velocity before and after generating fingers. Second, the average amount of first layer fingers and layers. And regularly used is fluidizer and acrylic volume ratio is 1.9 and thickness is 0.5 centimeter. And this is the velocity of first and second diffusion with different ethanol ink ratios. And this is average amount of fingers with different ethanol ink ratios. And the number in blue is the amount of layers of the medium. And our experiment 2, different fluidizer, acrylic volume ratios, and dependent variable, average velocity before and after generating fingers, and average first fingers and layers. And regularly used is a mix of drop of 20 microliters and ethanol in 1.5. And here is our velocity of first and second diffusions. And this one, the number in blue is the amount of layers of a medium and our analyze how different ethanol ink ratio affect. First, explosion velocity doesn't conform to expectation of more ethanol, more flowable. And second, diffusion velocity being extremely small and all close to 0.007 centimeters per second. And this is our surface tension values of some common test liquids. And how we measure? We drip the mixture 20 microliters with different ethanol ink ratio vertically drip it on a Petri dish and shoot the photo of a mixture in Petri dish. And use a protractor in tracker to analyze the angle. Why do fingers grow? Due to household flow and the tip building process of subplantar instability and other instabilities. What decide the approximate location of fingers? And it have a positive correlation with cosine theta surface tension mixture and the degree of flowable of the system.
Excuse me, time's up. So here comes the question from opponent to review for 2 minutes.
So here comes the questions from the opponent. So first, could you please turn to the graph? The graph. So you mentioned you only investigate the number of the first layer. Did you investigate the bigger numbers of the second layer or more? Yes or no?
Yes, we did a finger.
For the second and third.
Yeah, we
Okay.
did.
And so you said, do you think that 3 experiments is enough for showing the trend 3 times?
3 times. Yeah, I think it.
Okay. So could you explain the question to the page of theory? Could you explain why it will cause a fractal again? Yes, you.
The household flow happens in low viscosity liquids replace higher one in narrow gap, and subplantar instability is in unstable fluids interface in porous medium, and carbon holes instability is by velocity difference across interface.
So do you think that is a concentration difference between from here and here? Is that the one factor of the elements? By the concentration difference.
Subplantar instability.
Excuse me, time's up. The opponent, you got 3 minutes for preparation. proceed to discussion with the reporter.
Honorable juries and fellow commentators, I'm the opponent Jason Lee from the physics team student high school. And now I'm going to oppose problem number 1, metal fingers. So here's the problem statement. We want to investigate how the geometry and the dynamics of the fingers, which is formed by dropping the droplet of an ink alcohol mixture to a diluted acrylic paint. And here, the reporter mainly focused on the characteristics, like the layers, the numbers of the fingers, and some dynamics of the fingers. So here's the structure of the reporter. They used a video to show us the observation of the phenomenon, and also they used several theories like Mercalli effect, the segmentary instability, Helmholtz instability, and the Hell-Shaw flow. And they use everything, and the droplet is 20 microliter each time to use the setup. And then for the experimentation, they change the parameters like the EI ratio, which is the ethanol and ink ratio, and also the acrylic volume ratio. And for the conclusion, they showed us some relationships between the parameters. So here are some strong and weak points for the reporter. They first got a very clear delivery, and they're good at the analysis of the phenomenon, like the investigation of the layers. And they showed us the numbers of the fingers, and there's such a chain. But also there are some weak points. First, there are lack of different parameters in the investigation, like the thickness of the acrylic paint and more. And also there are lack of the relationship between the theory and experiments. Like they didn't show us why some of the parameters will lead to such results. And here comes to our discussion points. So, reporter, please.
Reporter, take the floor, please.
So, could you turn to the page which shows the video first? Here. First, some minor questions like does the ink, like a black area, is on the paper or on the petri?
It's on the petri.
So does that affect your color analyzing?
No.
Okay. So video, please. Or any picture that shows the fractals? Oh, okay. So first you define the inner circle, which is as a explosion. And how do you define the fingers? Like in this video, where is your finger started? So where is your fingers? Because I can't see quite so the small bumps. And can you show me like with other layers, like multiple layers? And then any picture? So how do you define the layers? If there's any second layer here?
Yeah.
Can you point it out?
Here is the first diffuse and here is the first and this is the second.
So how do you count the first diffuse number of the fingers?
Sorry, I can't explain this.
Fine. So is there any formula that shows the relationships between the EI ratio and the fingers of number of fingers or layers? In theory, of course. explain why the EI ratio affect the numbers of fingers?
Because they're in supplicant integration and they have to decrease the surface area to control a minimum of surface energy.
So you mean like, how is the fractional significance? Like the randomness of the central concentration or anything else? Like for the concentration, like what is the ratio? EI ratio? Like so because if the EI ratio is different, it will cause the ink will move up.
Yeah.
Yeah. So why only move up on the fractals but not whole circle? Like if it is evenly distributed, it will, in our point of view, it will spread like a circle that goes out. But why there are fractals formed? Like fractal forms because some of the quantities doesn't go out. So in our opponent's view, it is because when we drop the droplets, the molecules inside of it will spread randomly because we drop it. So then if it starts to spread, the difference between each point will cause a concentration difference, which causes the fractals to move up. Okay. Okay, please turn to the page that shows the theory, which is like good instability. Okay. Here, so what is what is this photo means? Like, what does it shows?
You may proceed to the next question.
Okay, fine. So please turn to the page that shows different layer numbers in your experimentation. Can you tell me why it will cause different layer numbers? Layer numbers, right? Yeah, that's one. Great. So why there is two hands? One, like what is the main reason that causes the amount of layers?
Because of the concentration, different concentration.
But what about here? Because for layers is that there's no boundary condition here, or there is. What is the main difference of parameters between 3 layers and 4 layers? Because I can see clearly in this graph. fine. And also, what causes the numbers of fingers? What parameters cause the difference of number of fingers? Instrumentation.
You mean a theory or?
Instrumentation, like, can you show us a significant difference between the significant relationship between the amount of fingers and any other parameters? So that's fine. So could you tell me how do you define the first layer and the second layer again? Is it by color or is it by the fingers or what else? Like first layer and second layer, what's the big difference between? How do we separate it?
Spreading velocity.
So in the second layer, the velocity is quicker or is faster or slower?
The second is slow.
Slower.
Slower.
So what causes the slower velocity? Is it the concentration or is it?
We have to. Because of the as law evaporates.
So in this unit, okay. So that would be the end of my discussion.
All right, Tony, you may summarize the discussion in
So
1 minute.
from the previous discussion about the definitions of the layers, the numbers, and also the relationships between the theory, like some of the concentrations, how does the concentrations do with the results, like the layers and the fingers numbers. So this will be the end of my summation.
All right, great, thank you. Questions from reviewer to reporter and opponent? Reporter, take the floor, please.
So first to the reporter, in the video shown, you showed that you used the pipette to drop the ink out of the picture. But the drop wasn't in one specific location, instead it was spread out. There were many points on the paint. Do you think this will affect your experiment?
No, I don't think it will affect.
What do you think?
I don't think it will affect, but we should still fix it.
Next is that you mentioned that gravity has an effect on the initial drop. So do you think that if you change the height of the drop, that your experiment results will have a difference?
Yeah, I think it will have a difference, but we didn't do an experiment.
For our opponent's view, we think that the drop will add the randomness when it drops to the paint, so it will affect.
And last is, when you were doing your experiment, did you control your temperature?
Yeah, I did control the temperature.
How did you control it? Did you control the temperature of the lab?
I control it with a box, so I put it in.
So everything inside was like controlled, not only the temperature, but the humidity and everything else.
Yeah.
And you just did it with the box, and you did everything inside the box.
Yeah.
And for every experiment, there was everything else.
Yeah.
How did you make sure that like everything was the same? How did you do it? you said that you used a pipette to drop it from above, but it was in a box. Then how did you manage to do this? If you go back to your setup, the one where you showed the pipettes. There's your setup, like the whole thing. Because you dropped your droplet from a pipette from above, but if that was in a box, then how did you? Yeah, see, because in this setup we don't see the box. So what does the opponent think of this?
We don't know about what is exactly what.
Excuse me. Hands up. Review, we got 2 minutes for preparation. All right, if you may take the floor for up to 4 minutes.
Hello, entrepreneurs and joiners. I'm Liu Yushen from Team Newgate, and today I'm doing the review for problem number 1, fractal fingers. So first of all is the problem statement. When you drop a droplet of ink alcohol mixture onto a diluted acrylic paint, fingers form, and we're supposed to observe the geometry and dynamics of the fingers influenced by the relevant parameters. For the reporter, their theory is that the ethanol acts as the polar solvent and the acrylic has lipids which causes them to interact. And it's affected by surface tension and the spreading coefficient. There's also flows and instability that are elements of this phenomenon. Next is their experimental factors. They changed the ratios of the ethanol and ink, causing different surface tensions. And their conclusion is that the finger grows due to instability of the two liquids. And the ethanol and ink ratio had to do with the spreading speed, but it wasn't as they expected. What we think the reporter did good on was they put error bars on their data graphs. They explained the theory behind the phenomenon very clearly, and they had to claim on their experiment. And that was really good because sometimes if that wasn't put on, then we could misunderstand some things. But in the video shown, the ink was not dropped on one specific place, and this will be discussed later. And when you're presenting, this is just a suggestion that you shouldn't be looking at your script in the presentation too much, because that affected our audience and the time management was a bit off. The opponent, we thought, did really good on summarizing the reporter's presentation, and the questions asked during the discussion was very targeted at crucial experiment points. And you could speak a little bit louder, and when the reporter couldn't answer a question, you shouldn't get stuck on one question. Next in discussion, there's one thing I want to point out, is why are there fingers that form? And the reporter wasn't able to answer this, but the opponent said that the molecules spread differently. Now, in our opinion, when the ink alcohol mixture spreads to a specific amount, the surface tension and the force between the two liquids are a bit unbalanced, which is a change from their initial balanced state. When this is unbalanced, it means that the outer perimeter of the ink alcohol mixture has different spreading speeds, which is basically means that their surface tension isn't the same at all points, and this will cause some to spread and some to stop. For the questions I asked about the ink that wasn't dripped onto one specific location, both of them don't think that it would affect, but they should fix it. But when we did the experiment, we found that this does affect it, because when the ink spreads when the big droplet of ink mixes with a small droplet of ink, it affects the surface tension, because it suddenly meets a surface tension that is similar to itself, and isn't similar to the acrylic ink. So this will be an effect on this. And next is, you mentioned that gravity has an effect on the initial droplet. Will changing the height affect its results? Both of the reporter and opponent said that it would. And we agreed on this, but only barely, since if the initial droplet manages to flow on top of the liquid, then it doesn't really matter. And for the last question, do you control the temperature? They said they used a box, but we didn't see it. But this would affect the results, as the ethanol acts as the medium to bring out and create fingers.
Excuse me, time's up. Here comes the concluding remarks from the reporter for 2 minutes.
And my summarize, I think I need to think more about problem statements and need to do more experiments like different parameters, and think more about how to define a finger, and to know more and clearly about a theory that can explain this phenomenon. And maybe we need to manage the temperature and better time management. And the ink need to drop on the one specific place and no script.
You done? All right, great. Here comes the questions from jury members. Please take the floor. Yes.
Okay, I would like to confirm your concept. Could you go to page 9? The question is, can the shear shock flow sustain the Kelvin-Helmholtz instability? Don't you think? Page 9. You say that the system is something like a PF2 cell. Can this kind of configuration sustain the Kelvin-Helmholtz instability? Or simply say yes or no? Okay. Okay. Then how about the concept of opponent?
We think yes, because the upper liquid, which is the ink and ethanol mixture, has a velocity, but the lower part, like the acrylic pen, doesn't have velocity, so it is surely a velocity difference.
Okay. And how about, do you agree with that?
We agree with the opponent, and we think that there is definitely a velocity difference in between the two liquids.
So you agree with that?
Yes, please.
Really, stop on the reporter. Can you tell me why the surface tension plus diffusion plus the stability prevent the finger growth? What's the physics behind it? Why all these factors combine together to make the finger grow? Okay, opponent.
We think that what she wants to say is the surface tension gradient that which is the S. So when S is bigger than 0, it will the gradient will become will tend to go out.
This is only like talking about if it will spread or not. And for the fingers, I think the fingers come out because in different points of the same liquid, the surface tension might not be the same.
Any other?
Okay, I have one more follow-up action. Yeah, about the segmented instability. Do you think the viscosity difference is a critical parameter? Let's assume the scenario that you have a very, very large spreading parameter, you have a very strong driving force. If the viscosity for the ink and the darkly ugly ink are the same, can this kind of instability be triggered? I mean, you have the very large driving force, such as, and the viscosity are the same for both kind of liquid. Can this kind of instability be driven?
You understand the question?
And if the viscosity for the upper and lower liquid are the same, viscosity are the same, even you have a very large driving force, can this kind of instability can be triggered? Yeah, ready?
I think no,
Why?
because there's no viscosity difference. So like I want to call it a friction force. There's
So which one, the viscosity, which one should be larger?
the lower one.
The lower should be larger? Okay. And how about?
When it reaches viscosity too low, if the acrylic paint reaches a viscosity too low, then the ink will just spread out circular because it won't have to go against the viscosity of the acrylic below. And if the acrylic is too high in viscosity, then the ink alcohol mixture's surface tension will not be able to go through the surface tension of the acrylic paint. So it won't spread and it will just stay as it dropped, as it was dropped.
All right, more questions? Yeah, there's this question. Sure.
One final quick question. The draw net is contained of two different mixture of liquid. Is it important or critical for the fingering draw?
We think yes, because it will affect the viscosity, the evaporation rate of the mixture.
And you also think yes because the ethanol acts as the medium that carries out the ink and the ink provides most of the viscosity.
What's that? All right, thank you. All right, lady. The score for reporter. Start from me. 4, 5, 5, 4, and 5. Score for opponent. Start from me. 6, 8, 7, 5, and 6. Score for reviewer. 6, 8, 7, 6, and 6. All right, I think pretty much even, so no comment needed. So with that, I'd like to conclude this fight. Thank you all.